Hello everyone. Let's start with this new topic called relative motion. Though it's not entirely new, but yes, we are going to learn here in this particular topic that how we will be studying that relative motion and what it exactly is. So let me link it with the things that we have gone through. We are talking about the motion basically, or we call it the kinematics. So kinematics or motion is going on. And in this we have talked about the case in which a particle moves on a straight line. So we have considered this case, let me draw like this. If we throw a particle in the upward direction, vertically upward, so it goes like this and return back. That means it follows a straight line path where this is the ground. And let's say if we throw a particle like this on that ground, that makes certain angle from the horizontal or vertical, you can say. So it falls like this. So that's a two-dimensional motion, that's a one-dimensional motion. Similarly, we can talk about the multi-dimensional motion, three-dimensional and all. But the point is, this motion is 1D, that means a straight line motion. This is a parabolic motion. How we are able to say? We are able to say because we have understood these motions. We have described the equation of path as well and all that thing, right? But if somebody asks, who says this? So that means with respect to what they have been claimed like this. So here we draw this ground or earth. So we say they have been claimed with respect to earth. That means any person standing on the ground is going to claim this thing, whatever we have made the claims till now. Similarly, all these claims will be made by a person standing on the ground. So that means these motions are relative to the ground, because we have already talked about all the motions are relative. There is no absolute motion except the speed of light. So you will find in normal life all the motions are relative, so there has to be some frame of reference. So here the earth plays a frame of reference. Similarly here also the earth is playing, or the ground is playing, the frame of reference. Right? So if nothing is mentioned, that means this is for granted as a frame of reference. Okay. Now let's take another example and try to understand the importance of this relative motion. So let's say you are moving on a train. So let's say this is a compartment and this is moving with certain velocity in this direction. And you are here. Let's say your name is A. And of course this is moving on the ground, and let's say on the ground there is another observer person, that's a B, maybe your friend. So these are the two persons, and we need to see the importance of relative motion over here. So let's say A does an experiment. What A does is this: A has a ball, and this ball is being thrown in the vertically upward direction. So it will go and return back to that person's hand. Let's say, so it's throwing in vertically upward direction. Now this ball is being observed by the two observers. One is A, another is B. Now if you imagine this kind of scenario, because you have seen this kind of scenario, you can easily imagine that is related to a practical life. Then if somebody asks what is the path of ball or trajectory of ball, so if somebody asks what is the path traveled by or covered by ball, path by ball, I am writing in short. Iska matlab, this meaning is basically we need to find the path that is traveled by the ball or trajectory of the ball. So if somebody asks what is that path, you will find it's an incomplete question. One has to say with respect to whom. You will find A will be observing a different path of the same object, same motion, and B is going to observe a different path because its frame of reference is different than A. This is earth, where this is a car or train or buggy, whatever you call it. So can you think of what the path going to be of this ball as per A? So you will say it's going to be straight line. A straight line, that means going to be just like this motion for the observer A. So a straight line with respect to or as per observer A. Not only observer, any person on the car is going to feel like the same, observe the same thing. That means this is basically with respect to car. Or we can call the name of the observer, both are going to have the same meaning, right? So here the frame of reference is a car and the motion is going to be a straight line. Is the straight line will be also for this observer? That means the person on the ground. You will find, no, that's not going to be the case, because when the time passes, then this person will reach somewhere there and this person will catch the ball again. But this person A will be observing that ball has gone upside and downside. But the person on the ground will be finding that the ball is going like this. That means for person on the ground, that's B, is going to be a different type of motion. It's not a straight line at all. So it's going to be parabolic or projectile. Parabolic path with respect to ground, earth, or observer. You can name the observer. Observer is B. So you see the same motion of the ball is different for two different observers, right? And this is because of the relative motion. That means the motion of ball relative to the car. That's one case. Then the motion of this ball relative to the earth. So on which reference we are looking the object's motion, that's very important. And we cannot say whatever the A is claiming, B is going to claim all the things same. Because since their motions, their paths are getting different, then we can think of their motions are different, entirely different. Hence, we need to learn how these motions are going to be when we change our frame of reference or we consider one frame of reference. Now, this was easily visualizable situation. Some situations might be very difficult. Let's say somebody is firing a bullet and this bullet is going to hit some target, let's say. So if this bullet is going to hit some target, so for this bullet you will find a target will be appearing coming towards the bullet, right? So how the bullet is going to see outside world is going to be different for us to visualize, right? Or maybe some spacecraft is moving in this space, how the things will be visible. For those things to understand, we need to know what the rules of relative motions are. How we get to know whether this is going to be straight line path and as per this is going to be parabolic path. So let's try to go inside and talk about the relative motion and the rules related to with this. And this relative motion is, all the motions are relative. This is also relative, this is also relative, but they are with respect to ground. So whenever with respect to ground or earth they are, we simply call them as a motion. But whenever this frame of reference starts making a difference, then we say that's related to that frame of reference, because earth is common for all of us. So now let's proceed and try to formulate the formula for relative motion. So in relative motion, mostly we will be using velocity. So how the notations go, let's talk about first notations. So let's say this is, I'm writing V as a vector. So when we write V as a vector, so we call it a velocity. Now let's say we are writing V A. That means we will read it as a velocity of A. And let's say we are placing a comma and writing B. So it will be read as a velocity of A with respect to B. So that's going to be the language we are going to follow. It will be indicating velocity of the object A as per or with respect to or with frame of reference B. So in short, we are going to write as a with respect to object B. So with respect to B, what is the velocity of A? That is given by this notation. Sometimes you might get this kind of notation as well, VA then slash B. We will also considering the same meaning of this as well. That means the first letter is going to talk about the object we are considering. Second is the frame of reference, right? And sometimes we are going to write like this, V of A comma G. If we are writing G, that means we are with respect to ground. And since this ground is so common, so sometimes we don't write even. So if somebody is writing VA, this notation will be meaning velocity of A, still is the velocity of A, but this time it's with respect to ground or earth. So if there is no second letter coming in, that means that is with respect to ground. And if the second letter is specified, that means that is particular frame of reference. So this is going to be notations. Now what the formula goes, let me write the formula first, and then we will be deriving and proving that formula, and then we will start using that formula. So what the formula says? Formula says if we are trying to find the velocity of A with respect to any frame of reference B, this can always be written as velocity of A with respect to a new frame of reference called C minus velocity of C with respect to old frame of reference that's called B. So this is a formula that helps us to find out the relative motion or relative velocity. So whenever we need to find the relative velocity of any object with respect to any platform, so what we need to do, we need to choose another platform and with respect to that find the velocity of that object and subtract vectorially the velocity of that frame of reference which we have chosen new one with respect to the old frame of reference. Alright, so that's the general formula. Now let's say C that we have considered as intermediary frame of reference, let's say that's a ground. So okay, I have changed this way, so it should be let me correct it, it's going to be plus. And there's along with this there's going to be another formula as well. Another formula is this: if we need to write velocity of B with respect to C, we can always write it as a minus velocity of C with respect to B. So that's also going to be a formula that is going to be valid in case of relative motion. So that means if we look at B with respect to C frame, it will have an equivalent opposite velocity as if you look at from the frame of reference of B and looking at C, and there's going to be minus sign, right? So this is going to be the case. So if we place this CB, then there's going to be plus, and if we want to place it DC, it becomes minus. So these are the two formulas. That's a basic one. We are shortly going to prove them. Now let's say we are rewriting this, so we can rewrite this in this manner as well. What is that rewriting is going to be? Is it going to be V A with respect to B is going to be equal to velocity of A with respect to C minus velocity of B with respect to C. So if we are keeping the C at the last or as a respect for the 2, then there has to be a minus coming. And if we are writing in this order, so that becomes plus. So these basically both are the same formula, and this is one of the formula that we are using. And let's say let's make them a bit simpler. Let's say this C is a ground. So let's say it's like a velocity of a ball with respect to train. So we can say this is going to be velocity of ball with respect to ground minus velocity of train with respect to ground. Right, so if C is a ground, so we can eliminate this C. So this can also be written like this in a simplified version, that the velocity of any object A with respect to B can be remembered as velocity of A minus velocity of B. As we have seen this notation, when we write velocity of A, that means it's a velocity with respect to ground. So we can choose any frame, we can choose even ground, or we can choose even any other frame, whatever we desire for. So that means this is very general formula, and that will be true for all the frame of references that we are going to opt for, right? And once we know this velocity, let's say we are sticking to this last formula that we have written over here. And if we need to find this relative velocity, what we need to do, we need to know the velocity of A as well as velocity of B. Then we need to go for the vectorial subtraction. And subtraction of two vectors we have already understood, so that concept has to be applied to get this answer of relative velocity. Okay, just like this, this is true for velocity, similarly is true for acceleration, and similarly is true for position. So let's prove this, and then we will take some example to understand this properly. For derivation, let's see, there's a particle, and that particle is here, or that's object P. This we are going to discuss about. That means we are interested in its motion, what this motion of this particular object is going to be. And let's say there are two frame of reference. One person is here on this. For this person, this is origin. Let's call it as a 0. And another person is here. For this person, 0 origin, or the reference is here, coordinates origin. So that's a O prime or O dash. So this is, let's say, S system of coordinates, and this is S dash system of coordinates. So dash or prime you can think of. So they might have their own velocities and they might be moving, and this object is moving, and this object, we need to study about this object with respect to this frame as well as with respect to this frame, and then we need to relate how these velocities and displacements are going to link with respect to these two frame of references. So let's say if we talk about with respect to O, if it or we can say with respect to S frame, then what you need to do, you need to draw a position vector. So this position vector is going to be basically running from O to the point P, and that will be with respect to S frame. Let's say we talk about the motion of this particle with respect to O dash frame. So in this O dash frame, you will find we need to join this as a vector that will be behaving like a position vector for the observer in the frame of reference, which is S prime. Moreover, let's say we are joining these 2 points as well, so there's going to be a position vector that is going to be with respect to these two. So that means with respect to O dash will be having this as a position vector. So I'm drawing 3 vectors, and these 3 vectors are going to form a triangle. So this triangular law of vector addition we can use over here. Let's denote them. So I'm denoting this OP vector as, let's say, R vector, but this is R of P point or P object with respect to S frame. Let's say we talk about this vector, this is position vector of object P with respect to new frame, which is S dash frame. And this position vector will be indicating position vector, this is going to be position vector of this S dash frame with respect to S frame. So these are going to be position vectors, and notation is very similar when we are writing this R P comma S. It means it's a position vector of point or object P as seen from or with respect to O frame, or you can say S frame. We can also write it as O. Similarly, R P comma S dash or S prime is going to represent position vector of the same point with respect to new frame S dash. And there's another position that we are considering is of S dash frame with respect to S. So that's going to be position vector of S dash as seen from S frame. Now these position vector can easily be linked using the triangular law of vector addition. When we use the triangular law of vector addition, we say this vector plus this vector must be equal to this vector as per the directions. So can we say it's going to be equal to position vector of P with respect to S is going to be position vector of P with respect to S dash plus position vector of S dash plus with respect to S, right? So that becomes the relationship among position vectors or locations, you can call it. If this is the relation among positions, we can differentiate both the side in order to get the relation among velocity. So when we differentiate, so it will become dr by dt, and they will have a corresponding the symbols. So dr by dt becomes velocity. So since dr by dt is a velocity, we can use this point and we can differentiate both the side. So can you think of this will convert into this type: velocity of P with respect to S is equal to velocity of the same point P with respect to new frame plus velocity of this new frame with respect to old frame. So this is the formula that we started with, or I have listed that this is the formula that it follows. The only thing here, P as S prime is coming, there I wrote as A, B and C. So that's the point. It says if we need to find the velocity of any point with respect to any frame, you find the velocity of that point with respect to new frame and then add the velocity of new frame with respect to old frame. And if you switch them or exchange them, then there is going to be a minus sign coming in. Now you can further differentiate it, because you know differentiation of velocity becomes acceleration. So in future, if there is a need for acceleration from the different frame of reference, so that's going to also be very helpful, and we are going to talk about this equation in Newton's laws of motion, that means in the next chapter. So it will say acceleration of P as seen from one frame is equal to acceleration of P as seen from the another frame plus acceleration of this another frame as seen from the old frame. So this becomes the formula for acceleration, and you can always exchange these subscripts that are there. Then there's going to be minus sign, because if you are standing on the ground and train is moving, then the person on the train finds you to moving in the backward direction. So this minus sign is coming because of this. Let's say this is a person A which is moving, and you are standing on the ground. So as per you, B, this A is going to move in this direction. But if you ask from this A, then he will find this B is moving in the backward direction. So what happens? These velocities are equal and opposite. So that's why we bring this minus sign. That means what I'm trying to say is this: velocity of A with respect to B is equal to minus velocity of B with respect to A. So that's also an important relation you need to keep in mind. So this is how the derivation goes. It's a very simple. This is triangular law of vector addition, then differentiation twice, and getting a relation among velocities, accelerations, and this position. Now this is going to be used in this kinematics extensively, and in Newton's law we will be using this, something called pseudo acceleration and pseudo force, that will be coming with because of this, and this is a relative motion concept. Let me take a few examples and try to apply this so that you can understand how this is being applied and what are the important points that we need to keep in mind. So let's begin with one example. Let's consider this example. It says a person A moves towards east with velocity 10 meters per second, and another person B who is moving towards west with a velocity 20 meters per second. We need to find the velocity of A as seen by B and velocity of B as seen by A. So in this example we will learn what the methods or methodology we are going to follow. There are going to be two ways of doing this question. One, following these I cap, J cap directions, because these are the vector quantities, or another will be using the geometrical approach, that means making the geometry, that means triangle and rectangle, whatever is being formed. So let's say first decide which is north, which is south. So let's say we are choosing our normal coordinates, this representation of directions, because here we need to deal with only with east and west. So this can work. So we can think of this as north and this is east, and we can simply say this is I cap direction and this is J cap direction. So J cap here is representing north direction, I cap is representing east direction. And then we can proceed with the information. What is the velocity of A? So we need to write velocity of A. So this velocity of A is going to be equal to 10 in the direction of east, that means I cap. What the velocity of B is going to be? So you can write the velocity of B. B is pointing towards west, so that means minus I cap. Hence we will write it as minus 20 I cap meter per second. So these are the two velocities. And in the first part we need to find the velocity of A as seen by B. That means we need to find velocity of A with respect to B, or as seen by B. And we have got to know this can be talked about with respect to ground, so it can become VA minus VB. VA minus VB, and this is VA, this is VB, so you can substitute over here. So it's going to be 10 I cap minus of minus 20 I cap. So ultimately it becomes 30 I cap. That means our answer is that with respect to A, velocity of B is going to be 30 meters per second, and that is towards the direction is a positive I cap, so that's the east. So we can answer is a 30 meters per second towards east. Makes sense? And similarly we can answer the second part as well. In the second part it is asking about velocity of B with respect to A, and we already know that they are going to be equal and opposite. That means magnitude will remain 30 but direction will become opposite, and we can check out of it as well. So it's going to be VB minus VA. as per the rule, and VB is minus 20 I cap, and VA is 10 I cap, so there's going to be minus, because of subtraction, so it's going to be minus 30 I cap meter per second, which we are going to call it as a 30 meter per second towards west. So this is traveling west, whereas this is traveling east. That means with respect to B, A is moving towards east. With respect to A, B is moving towards west. And this could have also be understood by a simple figure. So let's say we draw this kind of figure. This is A, or this is person or object A, which was moving in this direction by 10 meter per second. And there was another person or object B, which was moving in this direction by 20 meter per second. So by your common sense, you can think of what the A is going to observe. A is going to observe that B is moving in this direction, right? And with which velocity? 10 plus 20, that's a 30. So 30 towards west. And what the B is going to observe, that means A is moving faster in this direction, and that's going to be 10 plus 20, that's 30. So we can use this common sense as a rule or as a procedure, and it will help us to solve many questions. So what we need to do basically, when we need to find the relative velocity, so we need to have a vector subtraction. And whenever we do the vector subtraction, what we need to do, we need to change the direction of the second vector, because there is a minus. And then we need to add the two vectors together. So what we can say is a plus and with this minus. So we need to add the two vectors in which the second vector has to be reversed in direction. And then we can use the geometrical method of vector addition. So let's say this is the second method, and let's say we are trying this first part. And this first part is going to be, we need to find the velocity of A with respect to B. That's what we need to find. So if we are interested in velocity of A with respect to B, then we will consider B as our frame of reference. So B will come at rest. So we will say this is B. Now B is watching things. So B will find himself at rest. And what will happen to this A? So A will have its own velocity, what it had earlier. But the velocity of second, that is B, has to be reversed. First it has to be reversed. So you reverse it. So reverse direction is going to be this. And then add it up with this first. So we are going to add it up this. So with respect to B. So that is with respect to B. That's how the rule is going to be. So whatever the frame of reference we are choosing, we need to make that frame of reference at rest momentarily, and or that particular case, and see how the another thing is going to be behaved. So this will be finding himself or itself at rest, and as per this, A will be moving. And for that thing, whatever the velocity of A, maintain that. Give the velocity of B to A by changing its direction. So first change its direction and give, if you add them up, so that becomes 30 meter per second. Moreover, its direction is this. So you can get your answer as 30 meter per second towards east. That's what is this. Similarly, can you justify the second part by using this? If you are going to justify the second, so you need to come to with respect to this. So it will be momentary, this will be at rest. So change this velocity direction, give it to this. So it will become, as per A, you will find B will be moving 10 plus 20, that's 30, but in the westward direction. So this is going to be applicable for all the cases. You need to simply change the direction of the second and add with the first. If they are in the same direction coming, so we can add to it. If they are coming in the opposite direction, we can subtract the magnitude. If they are perpendicular, we can use all the rules of vectors that we have learned. Okay, so that's a very simple example, and you are able to use it. Now let's take another example, bit better than this. So another example is this. It says a person A, similar language, moves towards east. So again, it's moving towards east with velocity given. Another B is moving towards north this time, and velocity given. We need to find again relative velocity of A with respect to B, and then B with respect to A both. So here is going to be a solution. So I'm solving this first part. Second, you need to solve an answer. So they will follow the similar logic. Again, first we need to draw these directions, and we can say they are north, east, southwest only. So we can consider two-dimensional picture, and in two dimension, this is north and this is east, and the rest you can consider they are going to follow. Now where the object is, or person A is moving, that's towards east, Where the person B is moving, that's towards the north. There are two methods as we discussed. You can use the first one, I cap, J cap stuff. That's straightforward. And I'm trying to explain by using a second geometric method. So let's draw the velocity of A. So what the velocity of A is going to be? So velocity of A is this. Or let me draw here. A is moving like this. That's A. And how much velocity it carries? It carries 4 meters per second. Where is the B going? So this is the velocity of B. What is the velocity it carries is 3 meters per second. And what I'm trying to explain is the first part. So if we are talking the first part, so we need to find the velocity of A as seen by B. So we need to take the reference of B. That means B has to be at rest and the velocity of B has to be given to A. So let's say this was B, I'm drawing by a particle, or you can make a person. So this B has to be at rest. So what the picture for this is going to be, so draw this B. And so there is no velocity with B, that means B is in rest. So with respect to B frame of reference, B comes to rest. Now, maybe this seems you tougher to digest, but this is very simple. Let me give some idea. When we are on the earth, this is earth, right? When we are on the earth, earth appears for us to be stationary. And when you are on the train, let's say this is a train and train is completely closed, nothing is visible outside. If nothing is visible outside, then you'll find the train is appearing you to at rest. Right? If you look from the window, then you'll find everything else is moving backside, but the train is at rest. If there's no jerks and all that. Similarly, if you are in the plane, if you have that experience, then you'll find when you are on the plane and plane is flying out of the clouds, then you'll find it will appear as if nothing is moving. That means you are at rest. Whereas the plane is moving with a velocity like 1000 km per hour. That means whenever we take any frame of reference, that means with respect to, so that frame becomes at rest for the observer whosoever is here. So for that observer, that frame will not be moving. So B person is at rest, so B will find himself at rest. And what he will be observing about A, the observation of this will be given by this formula. The formula is VA minus VB. For that sake, what we are going to do, we are going to draw this A. So let's say A is here and this A is being watched by B in this case. So A will have its own velocity, whatever it had, that is 4 meters per second. But it will get one more extra velocity because of this relative. That means we need to change the direction of B first. So velocity of B has to be reversed. So let's reverse it and then add with this. So after reversing, we are adding. So it's going to be this way. So this will come another velocity on A as per B, that becomes 3 meters per second. So if you have understood these 2 points, that means with respect to whom we are working, that velocity has to be reversed and given to the objects we are watching. So that means as per B, A will have these 2 velocities. If these 2 velocities are with A, then we can find what the resultant velocity is going to be. So whatever the resultant of these 2 vectors is going to come, that becomes our answer. Until now, we have understood that this is going to be coming because of the addition of vectors. So let's say this is going to be the resultant. And this angle, let's say this angle is alpha. We can find this alpha, we can find this velocity. So this velocity of A with respect to B. Can you find what this velocity is going to be? Yes, there is a vector rules and the total angle is 90 degree. So for 90 degree vectors, you find VA comma B. That means resultant is going to be under root velocity of A square plus velocity of B square. And you will also write plus twice AB cos theta, since theta is 90 degree. So because of that 90 degree, cos will become 0. So you'll find this as a resultant. Or in 90 case, we have this as a resultant. We know that. Now VA is given to us as, that means VA means this velocity, VB means this velocity as a magnitude. So you'll find it's going to be square of 4 plus square of 3. So that becomes 5. That means for person B, the A will appear to move with a velocity 5 meters per second. Whereas for the person on the ground was finding that B is moving with 3, A was moving with 4. But this relative velocity came out to be 5. Moreover, for B observer, A will not be appearing to move towards east direction. Rather, its direction will be somewhere there, and this direction will be, of course, somewhere there, this direction. So that's the final direction. So you might be asked where that is moving. So we can say from east direction, alpha angle towards south, right? And what that alpha is, we can find that alpha. So let's find that alpha. So tan alpha becomes equal to this component divided by this component. You know that because of the vector laws, so this becomes 3 by 4. Whenever tan alpha is 3 by 4, then you can call alpha as 37 degree. That means the velocity of A as seen by B will be at 37 degree towards south from the east. So we can say, let me write the result. Result has to be written like this. So a first part result will be like this. Velocity of A as seen by B relative to B will be or is 5 meters per second. That's the magnitude. And at 37 degree from east towards south. So that's going to be our answer, final answer. So as per B, A will be moving at 37 degree towards south from the east direction, and with which velocity it will be moving? With 5 meters per second. If you have understood this, then you'll find we have mostly used the vector laws and simply one formula. That formula is this, that means relative velocity. Now there's a second part, so this I'm giving you as a homework. So you try the second part and give the answer in the comment section. And what you need to answer as a magnitude and a direction. Now direction becomes very, very important. So in this case we need to see velocity of B related to A. So make this A as a rest, give the velocity to this B, additional velocity because of this rule, and then find the resultant and its direction. Making sense? So in this video we got a basic idea about what the relative motion is and what the formula is, its derivation, and a couple of basic questions. And this motion will be continued in the next lecture as well, and there will be few types of questions that are coming based on the relative motion. We will be dealing those types of questions, first theory, then questions. Okay, so that's all for this video. Thank you for watching. Have a great time.